Board, New York City subway. 5.5 million people daily. You grab the pole, doors close, train accelerates into darkness. The car carrying you weighs 85,000 pounds, contains 20 miles of electrical wiring, 10,000 individual components, and required 6 months to build. This 60-foot steel box began as flat sheets in Nebraska cornfields, traveled through 2 factories across 1,200 miles, and survived testing that would destroy ordinary vehicles. One company builds every new NYC subway car, Kawasaki, operating facilities in Lincoln, Nebraska, and Yonkers, New York. How does 40 tons of steel become underground transportation for millions? Why does single subway car cost $3 million? Stay with us. You'll witness welding robots joining steel with surgical precision and discover Subway's shocking secret: the air hockey floor that lets 2 workers move 85,000-pound train car by hand. Kawasaki Motors Manufacturing in Lincoln, Nebraska occupies 733,000 square feet. Facility so large you could fit 12 football fields inside. This plant produces subway cars for New York, Washington, D.C., and other major cities. For NYC's R211 order, Lincoln operates 3 dedicated production lines running 24/7. The facility manufactures 22 cars monthly, 1 complete subway car every 33 hours. Walk the receiving dock where flatbed trucks deliver stainless steel sheets from ArcelorMittal and Nucor mills. Each sheet measures 12 feet by 40 feet, weighs 800 pounds. 1 subway car requires 50 steel sheets totaling 40 tons. The factory floor operates on technology found nowhere else in North America: air bearing system. The entire floor contains thousands of tiny holes releasing compressed air, creating cushion between floor and work platforms. Each 85,000-pound subway car sits on platform floating on air film thinner than credit card. 2 workers can push entire car anywhere in facility. The floor stays so flat, tolerances within thousandths of inch that it resembles polished mirror. This system provides ultimate manufacturing flexibility, allowing cars to move between workstations without tracks or cranes. Car body construction begins with laser cutting. German-made Trumpf laser cutters slice stainless steel with 15,000-watt beams, cutting through half-inch steel at 30 inches per minute. The laser follows computer patterns precise to 0.005 inches. Side panels, roof sections, floor plates, end walls. Every piece cut to exact dimensions. Burrs get removed through automated deburring stations. The steel, grade 304 stainless, contains 18% chromium and 8% nickel, providing corrosion resistance for 40-year service life in humid subway tunnels. Welding robots join the pieces. 6 Kawasaki-built robots work simultaneously on single car, each programmed for specific welds. MIG welding, metal inert gas, uses argon shielding preventing oxidation. The robots lay 3,000 linear feet of weld per car, moving at precisely controlled speeds. Watch robotic arm trace floor-to-wall joint. The weld bead forms perfectly uniform, penetrating through both pieces, creating joints stronger than base metal. Welders wearing auto-darkening helmets monitor every joint. One supervisor explains, "Robot makes perfect weld every time, but human checks every inch. We're building transportation for 5 million people daily." The car shell, bare steel skeleton, moves to assembly station where floor installation begins. Plywood subflooring goes down first, providing sound dampening and thermal insulation. Over this, workers install rubber flooring material designed for subway service. Slip-resistant, easy to clean, resistant to chemicals and fluids. The flooring attaches via adhesive and mechanical fasteners every 6 inches. Ceiling panels install next. White fiberglass reinforced plastic reflecting LED lighting. These panels contain 16 air conditioning vents per car, each precisely positioned for optimal airflow. Interior wall panels get mounted to steel framework. Each panel, formed from molded fiberglass, fits specific location. The panels interlock via hidden fasteners, creating smooth interior surface. Behind walls, workers route conduit for electrical systems. Every wire, every cable follows engineering drawings, specifying exact paths. The conduit protects wiring from vibration, moisture, and passenger contact. Installing interior panels on single car takes 12 workers 3 days, 96 man-hours of precision fitting. Electrical installation is where complexity peaks. Each R211 car contains 20 miles of wiring, enough to stretch from Lincoln factory to downtown Omaha. 3 master electricians and 6 assistants spend 2 weeks per car running wire. The wiring includes power distribution, lighting circuits, door controls, HVAC systems, communication systems, passenger information displays, and CBTC, communication-based train control. Every wire gets labeled at both ends with alphanumeric codes. Color coding follows strict standards: red for positive power, black for negative, green for ground, yellow for control signals. The main electrical cabinet, brain of the car, occupies space beneath seating. This cabinet contains 70 circuit breakers, 40 relays, 12 transformers, and computer control modules. Workers connect each wire to specific terminals, torquing every connection to exact specification. 25 inch-pounds prevents loose connections causing failures. Testing happens continuously. Multimeters verify every circuit. Megohmmeter tests insulation resistance. Must exceed 100 megohms between any circuit and car body. One electrical error could disable entire train, so triple checking is standard procedure. Door installation requires Watchmaker precision despite massive scale. Each car has 4 door sets, 8 individual panels. The doors, 58 inches wide, are 8 inches wider than previous generations, reducing station dwell time by 30%. Each door weighs 200 pounds, hangs on aircraft-grade bearings rated for 10 million cycles. Pneumatic actuators, powered by 100 psi compressed air, open and close doors in 2 seconds. The door edges contain rubber seals preventing finger injuries. LED strips around each door flash green when opening, red when closing. These lights contain 500 individual LEDs per car, controlled by dedicated microprocessor. Seating installation follows specific layout. Blue molded fiberglass seats designed for durability and easy cleaning. Yellow flip seats provide wheelchair space. Grab poles, stanchions, and handrails installed according to accessibility standards. The looped stanchions, unique design allowing multiple grip points, get welded to floor and ceiling, tested to withstand 500-pound side load. Digital displays mount above doors. 28 screens per car showing route information, station stops, and service alerts. Each screen connects via Ethernet network running entire train length. After 8 weeks in Lincoln, the car, still incomplete, loads onto flatbed truck for 1,200-mile journey to Yonkers, New York. Multiple cars ship weekly on specialized railcar transport trucks. The Yonkers facility, 250,000 square feet, occupies former Otis elevator factory. Here, final assembly transforms Lincoln-built shells into operational subway cars. The facility maintains quarter-mile test track, elevated rails allowing full-speed testing indoors. Workers install propulsion systems. Alstom-built Optonix traction motors, generating enough power to accelerate 85,000-pound car from 0 to 50 miles per hour in 30 seconds. 4 motors per car, each weighing 1,200 pounds. The motors connect to trucks, wheel assemblies containing suspension, brakes, and gearing. Brake systems use both pneumatic and electrical braking. Pneumatic provides emergency stopping. Electrical regenerative braking converts motion energy back to electricity, feeding power line. Installing and aligning propulsion system takes 5-person crew 1 week per car. Testing begins before car leaves factory. Static tests verify all electrical systems function correctly. Doors cycle 1,000 times. HVAC runs continuously for 48 hours. Every light, every display, every sensor gets checked. Then dynamic testing, the car runs on indoor test track, accelerating, braking, taking curves at speed. Computers monitor bearing temperatures, wheel alignment, electrical consumption, brake performance. The test track includes curve equivalent to sharpest turn in NYC subway system. Track engineers verify car navigates without derailment risk. 5 car sets get assembled and tested as complete trains. The open gangway R211T models, 20 cars featuring accordion connections allowing passengers to walk between cars, undergo additional flex testing. Workers measure gangway movement through curves, verifying seals maintain integrity. Sound testing measures interior noise levels. Must stay below 85 decibels at speed. Climate testing runs HVAC at temperature extremes. After passing all tests, the train gets final inspection. MTA representatives examine every detail before acceptance. Rejection rate runs 2%. Rejected cars return for correction, delaying delivery. Kawasaki entered U.S. railcar manufacturing in 1982, winning contract for NYC's R62 subway cars. Since then, the company delivered over 5,000 railcars to American transit agencies. The Lincoln facility opened in 2001 specifically for subway car production, utilizing techniques developed building Japanese Shinkansen bullet trains. The Yonkers plant, established in 1986, has produced cars for every major northeastern transit system. Completed R211 cars travel final miles to New York City via their own power or rail transport, arriving at Coney Island Yard or Pitkin Yard for 30-day acceptance testing. Transit workers operate cars on actual subway lines during non-revenue hours, monitoring performance. After successful testing, cars enter passenger service. The first R211A cars began service March 2023 on the A train. Open gangway R211Ts entered service February 2024 on the C line. Eventually, 1,610 R211 cars will replace entire fleets of R46 and R68 cars built in 1970s. Environmental impact shows interesting contradiction. Manufacturing subway car generates approximately 40 tons CO2 emissions, mostly from steel production and electricity consumption. However, one car serving 40-year life transports 100 million passengers, preventing equivalent of 20 million car trips. Net carbon savings exceed 10,000 tons CO2 per car over lifetime. The stainless steel body is 95% recyclable. After 4 decades service, retired cars get shredded, steel returns to mills, becomes new cars. Here's the secret we promised. Subway cars' 40-year lifespan means it outlasts almost everything else humans build. Your car lasts 15 years, your phone lasts 3. But subway car manufactured today will still be carrying passengers in 2065. That's why single car costs $3 million, because every component must survive 40 years of daily violence. Doors opening and closing 50 times per trip, 400 trips daily, 6 million cycles over lifetime. Electrical systems enduring temperature swings from freezing to 100 degrees. Structural steel flexing through millions of acceleration and braking cycles. The engineering isn't just about building strong car. It's building car that stays strong through 4 decades of punishment that would destroy normal vehicles in months. From Nebraska cornfields to Manhattan tunnels, the transformation completes in 6 months. Kawasaki's Lincoln and Yonkers plants represent capability concentration, decades of railcar knowledge, specialized equipment found nowhere else, and workforce expertise impossible to replicate quickly. That R211 carrying you through subway system contains work of 300 workers across 2 states in 6 months. Those 20 miles of wiring, 10,000 components, 3,000 feet of welds, all positioned perfectly, all tested thoroughly, all guaranteed to function for 40 years. You board, you ride, you exit, never thinking about the engineering miracle carrying you. But now you know. Nothing about subway car is simple. Everything is deliberate, tested, and built to outlast almost everything else in your life. Hold titanium, strong as steel but 45% lighter. It won't rust, won't corrode, survives temperatures exceeding 3,000 degrees. Every Boeing 787 contains 32 tons of titanium. Your hip replacement? Titanium. The Mars rover wheels? Titanium. This metal starts as black sand on Florida beaches, transforms through chemistry so complex only a handful of facilities worldwide master it. In Henderson, Nevada, 40 miles from Las Vegas, TiMet operates America's largest titanium mill, a facility so critical to aerospace that government considers it strategic national asset. How does beach sand become jet engine parts costing $10,000 per pound? Why does titanium manufacturing require more electricity than small city consumes? Stay with us. You'll witness the violent beauty of molten titanium glowing like miniature sun and discover the shocking paradox. Titanium is Earth's 9th most abundant element, yet costs more than gold to produce. Time at Henderson sprawls across 600 acres of Nevada desert, manufacturing complex visible from space. The main production building stretches half-mile long, housing forges that shake ground when operating. This single facility processes 15 million pounds of titanium annually, supplying 70% of Boeing's titanium needs plus Airbus, Lockheed Martin, medical device manufacturers worldwide. 800 workers operate around the clock, 3 shifts daily, never stopping. Watch the receiving area. Trucks arrive weekly from Gulf Coast processors carrying titanium sponge, porous metallic chunks resembling pumice stone, each batch representing 6 weeks of chemical processing. The sponge, shipped in argon-filled containers preventing oxidation, gets immediately transferred to sealed storage. Titanium's reactivity demands constant vigilance. Expose hot titanium to air and it burns spontaneously, unquenchable. The entire facility operates under strict protocols. No sparks, no contamination, no mistakes. One error could destroy million-dollar equipment and kill workers. The vacuum arc remelting furnace is where titanium is reborn. This massive chamber, 20 feet tall and 6 feet diameter, operates in complete vacuum. Any oxygen presence causes catastrophic contamination. Workers load titanium sponge mixed with scrap recycle into electrode molds, creating consumable electrodes weighing 6 tons each. The furnace chamber gets evacuated to 0.001 atmospheres, essentially space-level vacuum. Electric arc strikes between electrode and water-cooled copper hearth. The current, 20,000 amps at 40 volts, melts titanium at 6,300 degrees. Molten droplets fall into ingot mold below, solidifying layer by layer. The process takes 18 hours per ingot, consuming enough electricity to power 400 homes daily. Watch through observation port as titanium glows white-hot, brighter than welding arc. The light carries ultraviolet radiation. Direct viewing causes instant eye damage. The ingot emerging weighs 12,000 pounds, purity exceeding 99.9%. The cogging press transforms ingots into workable forms through brute force. This hydraulic press generates 14,000 tons of pressure, equivalent to stacking 7,000 cars on single point. The titanium ingot, reheated to 1,800 degrees in induction furnace, glows orange when positioned under press. Operators work from shielded control room, manipulating ingot via robotic arms. The press descends with earth-shaking impact. Each strike reduces ingot thickness by inches while increasing length. The titanium screams, metallic shriek as crystal structure deforms under impossible pressure. Workers rotate ingot 90 degrees between strikes, ensuring uniform reduction. The process requires 48 heating cycles and 200 press strikes over 12 hours. What was cylindrical ingot becomes rectangular billet suitable for rolling. The precision is remarkable despite violence. Dimensional tolerances remain within 0.05 inches across 20-foot length. Hot rolling mills shape titanium into plates, bars, and sheets. The billet, maintained at 1,700 degrees, passes through series of roller stands, each applying progressively greater reduction. The rollers themselves, made from high-speed tool steel, wear out monthly despite water cooling. Titanium's abrasiveness destroys ordinary metals. The mill building vibrates continuously, low-frequency rumble felt in bones rather than heard. Watch the titanium emerge, glowing ribbon extending at 15 feet per second. Scale: titanium oxide forming on surface, flakes away in showers of sparks. Workers monitor thickness using laser micrometers accurate to thousandths of inch. Any deviation triggers automatic adjustment. The plate exits at quarter-inch thickness, cooled via air blast to 800 degrees before transfer to finishing area. This single rolling operation produces material worth $2 million per batch. Precision machining happens in climate-controlled clean rooms where temperature varies less than 2 degrees. Titanium's properties, low thermal conductivity, high strength, make it notoriously difficult to machine. Cutting tools overheat rapidly, dulling within minutes. The facility uses carbide-tipped tools cooled by pressurized coolant flowing at 50 gallons per minute. Each Boeing 787 wing spar requires 200 hours machining from solid titanium billet. CNC mills operate continuously, removing 80% of material as chips. These chips, valuable as raw material, get collected for recycling. The machining bay contains 40 CNC mills, each costing $3 million. Operators monitor multiple machines simultaneously, changing tools and verifying dimensions. A single programming error could destroy part worth $100,000. The facility maintains zero defect requirement. Aerospace applications tolerate no margin for error. Parts get triple inspected using coordinate measuring machines, accurate to millionths of inch. Quality control involves destructive and non-destructive testing. Ultrasonic inspection sends sound waves through titanium, detecting internal defects invisible to naked eye. Voids, cracks, inclusions, any imperfection appears on computer screen. X-ray fluorescence verifies chemical composition, ensuring no contamination from iron, carbon, or other elements degrading properties. Sample coupons get pulled from each batch for tensile testing. Hydraulic machines pulling specimens until they break, measuring ultimate strength. The testing laboratory maintains records on every ingot produced since 1950. Each piece of titanium carries pedigree, chemical analysis, mechanical properties, processing history, traced from beach sand through final product. This documentation follows material through entire supply chain. When aircraft manufacturer receives titanium part, complete history accompanies it. The traceability isn't bureaucracy, it's survival. Component failure at altitude kills people. The quality system prevents that. Timett's Henderson facility began operation in 1951 as Titanium Metals Corporation of America. Cold War drove expansion. Military aircraft demanded titanium for speed and performance. The SR-71 Blackbird contained 93% titanium by weight, enabling Mach 3+ speeds. Commercial aviation adopted titanium in 1960s as Boeing 747 entered service. Medical applications emerged in 70s when surgeons discovered titanium's biocompatibility. Human bone fuses directly to titanium implants. The Henderson plant survived industry consolidation, multiple ownership changes, bankruptcy restructurings. In 2023, Precision Cast Parts acquired Timt, integrating it into aerospace supply chain. Today's facility bears little resemblance to 1950s operation. Automation replaced manual labor. Computer control optimized processes. But core challenge remains unchanged. Transforming reactive metal into reliable material requires uncompromising precision and perpetual vigilance. Environmental impact seems paradoxical. Producing titanium generates significant carbon emissions, mainly from electricity consumption during vacuum melting. The Henderson facility uses 500 million kilowatt-hours annually, equivalent to 50,000 homes. Yet titanium's properties enable lighter aircraft burning 30% less fuel over lifetime. A single Boeing 787 using titanium structure prevents emission of 1 million tons CO2 versus aluminum equivalent over 30-year service life. Here's the secret we promised. Titanium is absurdly abundant, Earth's 9th most common element, yet harder to produce than platinum. The metal's extreme reactivity means it cannot be smelted like iron or copper. Traditional metallurgy fails completely. The Kroll process, vacuum arc remelting titanium sponge, remains only viable production method despite being invented in 1940. We're using 75-year-old technology because nothing better exists. Every attempt to improve efficiency fails against titanium's fundamental chemistry. From Nevada desert to Boeing assembly lines worldwide, the transformation completes. Timett Henderson represents industrial capability few nations possess, the knowledge, infrastructure, and precision required to master titanium. That jet carrying you across oceans depends on metal processed in this desert facility. The hip implant restoring mobility came from Henderson furnaces. We've built aerospace dominance on metal that fought us every step, that demanded we develop entirely new manufacturing processes, that cost fortune to produce despite natural abundance. Titanium doesn't compromise. Neither does Henderson. The facility runs continuously, glowing furnaces melting metal that makes modern aviation possible.
Hold a car battery. It weighs 40 pounds. 30 of that is pure lead. Every year, humanity produces 11 million tons of this heavy, soft metal. Romans used it for plumbing 2,000 years ago. We banned it from paint and gasoline because it poisons children's brains. Yet we can't quit it. Lead stops X-rays dead, stores electrical energy better than any alternative, and possesses one superpower no other metal can match. How does rock containing lead sulfide become the shields protecting radiologists? Why do we mine fresh ore when mountains of old batteries exist? Stay with us. You'll discover why lead is simultaneously essential and deadly, and the shocking secret making it the most recycled material on Earth. 99% returns to use forever.
Our story begins in Missouri's Lead Belt, America's primary source. Unlike flashy gold mines, lead operations look industrial, almost boring. Massive drills bore 800 feet down, following veins of galena, lead sulfide ore appearing as metallic gray crystals. Each ton of ore contains just 3% lead. The rest is worthless rock requiring removal. Underground, miners work in perpetual darkness, drilling blast holes into rock faces. The lead content makes galena unusually dense. Lift a basketball-sized chunk and it weighs like a bowling ball. You feel lead before you see it, explains one miner. Galena has this heft that surprises you every time. Explosives fracture the ore. Loaders scoop rubble into trucks, climbing back to surface through spiral tunnels, taking 20 minutes to traverse.
Topside, the crushing begins. House-sized jaw crushers reduce boulders to gravel, while workers monitor from control rooms behind thick glass. Lead dust is insidious, invisible particles that accumulate in bones, causing damage that appears years later. Modern facilities employ enclosed systems, but older operations tell different stories. Walk through a 1970s lead smelter photograph. Workers in street clothes, no respirators, covered in gray dust. Many develop neurological problems by age 50. The industry learned hard lessons about lead toxicity. Today, air monitoring systems track particle counts continuously. Workers shower before leaving. Clothes stay on site. Blood tests happen monthly. One manager puts it bluntly: respect lead or it destroys you. There's no middle ground.
The ore enters roasting furnaces heated to 1,400 degrees. Here, sulfur burns away as sulfur dioxide, captured and sold to sulfuric acid manufacturers. What remains is lead oxide, a yellow powder looking harmless but deadly if inhaled. The roasting building operates under negative pressure. Air flows inward, never outward, preventing escape of lead-contaminated atmosphere. Watch the roasting process through observation windows. Yellow flames dance over tumbling ore. Operators adjust oxygen flow constantly. Too much air, lead oxidizes excessively. Too little, sulfur remains. Getting it wrong costs millions in lost efficiency. The roasted material, called calcine, moves to smelting via enclosed conveyor belts. Nothing touches open air. The paranoia about containment isn't regulation theater, it's survival. Lead contamination cleanup can bankrupt companies.
Blast furnaces reduce lead oxide to metallic lead through carbon chemistry. Coke, purified coal, burns at 2,000 degrees, creating carbon monoxide that strips oxygen from lead oxide. Liquid lead, melting at just 621 degrees, pools at furnace bottom. Picture the tap. Workers drill through clay plug. Molten lead, silvery and dense, flows into molds, creating 90-pound ingots called pigs. The metal moves like mercury, forming perfect spheres when droplets fall. Lead's density is deceptive. A 5-gallon bucket filled with lead weighs 200 pounds, impossible to lift. Ancient Romans made lead pipes by pouring molten metal into sand molds. The same basic process works today because lead's properties haven't changed in millennia.
Refining removes impurities through clever chemistry. Adding zinc causes copper to rise as dross skimmed off surface. Calcium treatment removes silver. Lead and silver frequently occur together geologically. The final product achieves 99.99% purity. This refined lead feeds manufacturing plants producing batteries, radiation shielding, and specialized applications. But here's where the story shifts. Increasingly, smelters don't process mined ore, they process old batteries. Secondary smelters, as they're called, have grown to dominate the industry. Why mine lead when every dead car battery contains 20 pounds ready for reuse? The economics are brutal. Recycled lead costs 40% less than mined lead. Primary smelters struggle competing. Many shut down, unable to match prices of operations running on discarded batteries. Battery recycling begins at collection centers, where mechanics and scrappers deliver exhausted batteries by the thousands. Workers drain sulfuric acid into neutralization tanks. Each battery contains about 2 gallons of corrosive liquid that can't enter recycling stream. The acid gets neutralized with lime, creating calcium sulfate, sold as drywall ingredient. Nothing wastes. Drained batteries move to breakers, rotating drums with internal hammers that shatter cases, separating lead plates from plastic housings. It's violent. The noise resembles continuous demolition. Lead plates sink in water, plastic floats. Simple physics achieves separation. The plastic gets washed, shredded, and sold to manufacturers making new battery cases. The lead plates, still coated with lead oxide from battery chemistry, head to furnaces for smelting. One facility processes 50,000 batteries daily, enough lead to manufacture 12,000 new batteries.
The smelting of recycled lead mirrors primary smelting, but operates at smaller scale with tighter controls. Furnaces melt battery plates at 1,000 degrees. Impurities rise as slag, skimmed continuously. The molten lead flows into casting machines, producing standardized ingots shipped to battery manufacturers. Here's the remarkable part. A battery recycled today will be back in a new battery within 30 days. The loop is that tight. And that battery will get recycled again in 3 years when it fails, and again and again. Lead never wears out. Its atomic structure remains unchanged, regardless of how many times it melts and resolidifies. The lead in your current car battery might have started life in Roman plumbing, been refined into medieval type, reformed into ammunition, and now cycles through automotive batteries. Lead is functionally immortal.
Lead's history intertwines with civilization's darkest chapters. Romans sweetened wine with lead acetate, called sugar of lead, not knowing it caused madness in emperors. Medieval alchemists poisoned themselves studying it. The gasoline industry added tetraethyl lead as anti-knock compound in 1921, despite knowing its neurotoxicity. For 50 years, automobile exhaust sprayed lead over every city, poisoning children and causing measurable drops in IQ. The phase-out began in 1970s as evidence became undeniable. Removing lead from gasoline represents public health's greatest victory. Childhood blood lead levels dropped 90%. Paint bans followed. Today, lead use concentrates in batteries, radiation shielding, and specialized industrial applications. We've learned to respect lead's toxicity while exploiting its unique properties. The metal that once poisoned Rome now powers modern transportation, but safely, contained.
recycled endlessly.
Carbon emissions drop 72% producing recycled lead versus mining virgin ore. Industry saves $63 billion annually through battery recycling. Processing scrap uses 65% less energy than conventional smelting. Here's the secret we promised. Lead achieves 99% recycling rates, the highest of any industrial material. That car battery has a 99% chance of being recycled properly because it's worth money. Scrappers pay you for dead batteries. Mechanics collect them religiously. The economic incentive creates a closed loop more efficient than any regulation could mandate. From ancient Rome to modern recycling, the transformation completes. We've learned that some materials are too valuable to discard, too dangerous to mishandle, and too useful to abandon. Lead will never be green, but it might be the perfect example of circular economy functioning through market forces. That heavy metal under your hood has been serving humanity for millennia. It'll still be serving our descendants centuries from now, because lead never truly dies. It just waits to be reborn.
The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships. Everywhere, zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground. Darkness. Explosion. Tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant,
Concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint.
For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use. But its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible.
70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousands of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Marggraf in 1746, but mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know, they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level. How one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit. Dense as lead, but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised: every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer greenskin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home.